what it was. Okay, so this is this argument for why the maximum point of the spectral energy density differs in the wavelength picture and the frequency picture is because the spectral energy density is defined with respect to a unit quantity, whether it's a unit wavelength or a unit frequency. And the size of this unit is, of course, different. So a unit wavelength is not the same as a unit frequency. So that is why the point, the maximum you get from the two pictures, they are different. No, I am not presenting yet. So that sort of concludes the black body radiation in a way. There is one more part which I will give you as an assignment. Okay, and I'll give you a week's time to complete it. So today,
ma'am, I just had one question before that. We found out nu max from the same intensity equation, but since nu times lambda is c, which is constant, why is the lambda found from that way? I mean, you are saying that the only difference is the difference in units, but I
no,
am
the
asking
difference is in the problem is in the difference of the definition of the spectral energy density.
okay.
The spectral energy density is defined per unit wavelength or per unit frequency. So the maximum of a quantity which is per unit of like something else, they are not necessarily the same. So
that's why, ma'am, we had to multiply them, not that d lambda and d nu to equate them and convert them.
Yeah, exactly. So if you had done, if you could have done some sort of calculation with including the d lambda and the d nu, that would have been the same. But unfortunately, that you cannot find a maximum of that quantity or a minimum of that quantity. That is not feasible if you have a d lambda or a d nu in your expression. So just so it's an interesting point. So it's good to note that whenever you have some quantity which is per unit something, then you have to be a little bit careful when you just shift around variables or change the variables. Okay. They may not always lead to the same thing. Okay, the last thing that we have left is reproducing Stefan Boltzmann law. Now, I believe you are all aware of the Stefan Boltzmann law. It tells you how the total radiation emitted by a body depends on temperature. So it's basically U is equal to sigma T to the power 4. But, and this can also be actually derived from Planck's law. So I'll give you all the relevant details in the assignment question. I'll put it on VLearn, and then you can do it as an assignment. Okay. And today we will go over to other phenomena or other experimental phenomena which could not be explained by classical physics, and we had to go over to quantum physics. So let's talk about light-matter interaction. Now, light-matter interaction can be both classical and quantum. I mean, ideally, of course, it's a quantum phenomena, but a number of the phenomena can be explained classically, and some could not be. So let's list some of them. This is not all the possible interactions, just some examples. So there is the photoelectric effect, which is the emission of bound electrons by radiation. So when you have light falling on a metal typically, then electrons are emitted. Now this could not be explained classically. This is a quantum phenomena. But then there is something else called Thomson scattering, which is the scattering of light by free electrons when there is no change in wavelength. So if you have a red light of certain frequency falling on this metal and it's scattered, there is a change in the direction of the light, but there is no shift in wavelength. This can be explained classically, simply with wave theory. Then you can have Rayleigh scattering, which is the scattering of light by bound electrons or atoms, like the entire atom. There is no change in wavelength. There is only a scattering of, or scattering means basically change of direction of incident light. This can also be explained classically. And then there was a fourth phenomena which was discovered much later. I mentioned it in the timeline, if you remember, which is called Compton scattering, which is the scattering of light by free or loosely bound electrons with rebound of electron, meaning, well, it's scattered, so it changes direction, but the light also shifts in wavelength. Okay. Typically, there is a red shift, which means that its wavelength increases. Like what if you have, let's say, red light incident on some free electrons or loosely bound electrons, maybe you get orange light that is reflected off, okay, in addition to a change in the direction. Now this required again a quantum explanation, and if you want to be very accurate, you also had to include relativity and QED. QED means quantum electrodynamics, where light is also treated quantum mechanically. So we will do photoelectric effect and Compton scattering, since these are the two quantum phenomena. The classical ones, we just let them have classical explanations. They will not be part of the course. So first, so today we'll do something that's simple and you have done before. This is the photoelectric effect. So what is basically the phenomena? The phenomena is that you have a metal. So there is a metal surface and light is incident on this metal surface. And this results in emission of electrons. These electrons can be collected by a detector. And if you have a current detecting mechanism or an ammeter connected to it, you will record a current, which means that the detector is collecting electrons and the circuit is getting completed. When the light is off, then the circuit is broken and you don't collect the current. Okay. And there are, of course, so additional observations which we're coming to. I'm just referring some YouTube videos which show very nice animations and explanations. So I had set them up in the last semester, but some of the videos are gone. So I was checking them today and it says no video found. So then you just ignore it, okay, if it's like that.
Ma'am,
yeah.
answer the question.
Yeah, sure.
So in the photoelectric effect, I understood like the whole process, like you shine light of one frequency and then the electrons are released. But then like how are they detected? I didn't understand.
You connect an ammeter to the circuit and you see that the current is, there is a current in that circuit. You directly detect. So when the electrons are collected by the detector, then they move through the wires, and then if you have an ammeter in that circuit, it will detect a current.
Okay. Yeah.
Yeah. So the electrons are basically completing this current circuit. Otherwise, it's like a switch. So when you switch off the light, the circuit is broken and there is no current in the circuit.
Ma'am, why is there a battery?
The battery maintains a potential. So it keeps the metal surface at a negative potential relative to the detector.
Oh, but we'll see this effect even if there is no battery, right? Or
if there is no battery, then you would only get a momentary current, which is difficult to detect. So what the battery does is it keeps supplying enough electrons to the metal surface so that it can be emitted by the surface when light is incident on it. So if you just had a metal, then you would just have, few electrons and then stop. Metal would become positively charged, and it would not emit any more electrons.
okay.
Okay. So the detailed observations of the photoelectric effect, which were actually what you wanted to explain, are the following. So there were two studies. So one is where you change the applied, one is where you change the intensity of the light. So you are basically shining more and more light on the metal surface, and you are measuring the current against the voltage applied. So like we spoke about the battery, so there is a voltage applied here which we can change, right? This is a battery, and I am plotting the current in the circuit against this voltage. So I have fixed a certain range of voltage in which I will do this study. And in addition, I'm repeating this experiment with 3 different intensities of light of the same wavelength. Okay? So the frequency is constant. I have 3 different intensities, and I am plotting the current versus the applied voltage in some range. Okay, and this current is basically called the photocurrent because it is generated by the incidence of light. So what is our observation? So before I talk about the observation, let me tell you what V stop is. So when the detector is positive, then it will collect any and all electrons that are emitted by the metal surface. Okay. But when you make the detector more and more negative, then it will stop collecting the electrons. It will eventually stop collecting the electrons, right? So, because it repels them. And that is what you see here, that when the voltage is positive, so when it is in this range, then you basically get the same current. So concentrate on any one plot. Let's say this is light with an intensity I0. I'm not sure what this symbol is, okay, but it denotes the intensity. So the lowest plot is for an intensity, let's say I0, and this is twice the intensity and this is thrice the intensity. So let's just concentrate on one plot, okay. Then when the applied voltage on the detector is positive, then you get the same current for the full positive range of voltages, because even if it is slightly positive, all the electrons will get attracted. Okay. But when it becomes negative, then slowly the current falls, which means fewer and fewer electrons are able to make it to the detector. And I hate this. Okay. And eventually you come to a certain negative voltage which stops any electron from reaching it. Okay? So it is so negative that the electrons cannot reach the detector. This voltage is called the stopping potential. Okay. Now let's consider all 3 plots. So when we consider all three plots, we see that the amount of current increases when you increase the intensity. For the lowest intensity, it's this much. Then when it's doubled, then the current roughly doubles. And then when it's 3 times, then the current is also 3 times. Okay. But the stopping potential remains the same. Okay, so this was one set of experiments. The intensity dependence experiments, let's call them. Then the next set of experiments was, you keep the intensity the same, but you change the frequency of the incident light. Okay. So, and then again, you do the same, you record the same thing. You record the current for a range of voltages. So what is the observation? The observation is that when the voltage is positive, then you get a certain fixed current, irrespective of what frequency of incident light you have used. So we have used 3 frequencies of light, F1, F2 and F3, where F1 is the highest frequency. So the positive part gives you the same current. Then you are making the detector negative, so it is not allowing all the electrons to reach. Okay. But then what happens? Then when you have the light of the lowest frequency, which is F3, then the stopping potential, or the voltage required to prevent any electron from reaching the detector, that is the lowest. So the light of low frequency emits electrons which are easily stopped. The higher the frequency, the more the stopping potential or stopping voltage necessary to prevent current. Okay. So these were 2 sets of experiments. Now, why were they contrary to the classical picture? So classically, light carries wavelength energy through its intensity. The more intense the light, the higher the energy it carries. So then, what should have been our observation? Our observation should have been that the energy that could be transferred to the electrons by more intense light should be more. So more energetic electrons should be emitted by more intense light. Okay. And also, classically, the frequency of light was not related to its energy. Okay. So the frequency should not make a difference. As long as that frequency could emit the electron, the energy of the emitted electron should not have changed, whatever the frequency. Okay. Because you see, if it's a wave, then an electron could, wait and absorb as much of the waves as necessary for it to be emitted, and then it got emitted. So if there is more intense light, then it can gain more energy in the same time. Okay. So this is very loose and rough language, but I don't want to go into the classical theory of in detail, so that's why I try to explain it as intuitively as possible. Okay. So if it was just the wave picture, then what should have happened is the stopping potential for various intensities of light should have been different. Okay. And the frequency should not have had any effect on the stopping potential. Okay. So, but the observations were different. So how was that explained? So this is what Einstein explained, of course. So he proposed that the energy of the light was related to its frequency. Okay. and which meant that the higher the frequency, the more energy the emitted electron had. And the intensity was simply it was the number of photons that were supplied. So Einstein said that the energy packets in the light can be called photons. Okay, so the units of energy, and the energy of this photon depended on its frequency, and intensity is basically the number of photons that are incident per unit time on the metal. So that is what Einstein proposed, and that can explain these observations. How? Let's see. So let's say in order for this electron in the metal to get emitted, there is a minimum energy, E phi. Okay. So this is in a metal, so they are loosely bound, but there is a binding energy, so that has to be overcome. And this binding energy is a characteristic of what metal you are using. So this is E phi. E is the charge of the electron, and phi is what is called the work function. So that has the unit of a potential. And so charge into potential is energy, and E phi is then the binding energy. So that much energy is necessary to free the electron, and then whatever excess is available in the photon, that is transferred to the electron as its kinetic energy. Okay. And Einstein said that every electron absorbs only one photon. Okay, why is that? Because this is a question of probability. So it can absorb 2 photons, but it is more likely to absorb 1 photon because there are so many electrons, and then the light is incident very fast, right? And it's most likely for that 1 electron absorbs 1 photon. Okay, which means that the excess kinetic or the total energy of the photon is used to overcome the binding energy E phi, and the rest becomes the kinetic energy. Okay. And it is this kinetic energy which determines how much stopping potential is necessary to stop this electron. Okay. So, okay, I'll come to the, yeah.
Can you again tell about that 2 or more photons can be absorbed by an electron? Means that part again.
Okay, so this is I just want to say that in the explanation for photoelectric effect, Einstein assumed that every electron absorbs only 1 photon to get emitted, but it is possible. I mean, it is not impossible that it absorbs 2 or more photons, but it is highly unlikely. So what you see in experiments will come from 1 electron absorbing 1 photon. So this is just a simplification, a justified simplification. Otherwise, you could have NH nu. So some NH nu equal to half mv square plus E phi. If you allow.
To ask that you said that due to some conditions only it is highly unlikely, that part.
I just said that it's a probabilistic thing. That the probability that 1 electron will come across 2 photons in quick succession, sufficient for it to absorb it, that is unlikely.
Understood. Thank you.
Yeah. Okay. So what was I saying? Yeah. So this kinetic energy of the electron tells you how much stopping potential is necessary to stop it. So if it is highly energetic, then it can overcome the repulsion from the detector and reach it. Okay. But if it is not, then it will stop. It will not reach the detector. So that is, and if you, then the stopping potential is basically the energy of the most energetic electron, right? So when there is no electron reaching, it means that even the most energetic electron is not able to overcome the stopping potential. Okay. And this will be exactly the quantity that is occurring in this equation. So why do we have a range of kinetic energies for the electrons? That is because some can get retarded while it gets emitted from the metal. So ideally, if you have a photon of frequency nu and energy h nu, the work function for all the electrons being the same, then all electrons should have the same kinetic energy. But that is not true in reality, because these electrons, in the course of being emitted, many of them can lose some energy, some kinetic energy. But the stopping potential will tell you exactly the kinetic energy of the most energetic electron, which you can assume obeys this relation. That it is the difference between the energy of the photon and the the binding energy of the metal. Okay. Fine. So it is the kinetic energy of the fastest electron. That is given by the stopping potential. And at any point, at any other point of negative voltage of the detector, any electron which has energy more than EV, so if V is the applied negative potential, then any electron with kinetic energy more than EV can reach the detector. Okay. So this is the explanation proposed by Einstein. One other thing is that in order to conserve momentum, the lattice, or which is the metal lattice, it also recoils, but since it has very much larger mass than the electrons, the recoil velocity is negligible and the energy that the lattice carries is negligible. So in case of photoelectric effect, the lattice recoil is neglected. Okay.
Ma'am,
So this is, yeah.
could you just explain this recoil part once again?
Yeah, so when the electrons are emitted from the metal, the lattice should also recoil in the opposite direction by moving in the opposite direction, because momentum has to be conserved. However, because the lattice is so much heavier than the electron, the recoil velocity of the lattice is very, very small, which means that a very small part of the energy actually goes to the lattice in case of photoelectric effect. So why I mentioned this is because in Compton effect, you have to really consider the recoil, because there the recoil is of a single electron, and then that then the energy that is transferred to that electron is no longer negligible. But in case of photoelectric effect, since this is a full metal lattice with a very large mass, the proportion of energy that goes to it is very small, so you can neglect it. Because we have not considered that in our expression, right? We've just considered that the electron is taking some part of the energy of the photon to overcome the binding energy and get emitted. So this is a much simpler picture because we are ignoring the lattice. Okay. Got it?
Yes, ma'am. Thank you, ma'am.
Yeah. Okay. So this is the explanation. using the concept of photons. And so the frequency dependence experiment is then clear, I guess. So the more the frequency of light, the more the kinetic energy the emitted electron has, so higher the stopping potential. Okay, so the second one. And for the intensity dependence, the more the number of photons incident on the metal surface, more the number of electrons emitted. So the magnitude of the current increases. However, the energy of the fastest electron is still the same because the frequency is the same in all three plots, and h nu minus E phi is the same quantity. So there is only one stopping potential irrespective of the intensity. Okay. Then with this explanation, we also get a method to determine phi. So what the work function is for a metal is not known beforehand, but you can find it out. So how do you find it out? So you basically plot the stopping potential versus frequency. So basically you are taking data from this frequency dependence plot. Okay. So from here you would get 3 points. So stopping potential for frequency 1, stopping potential for frequency 2, stopping potential for frequency 3. Okay. Like this, you do it for a range of frequencies. So here you see Mulliken did it for 1, 2, 3, 4, 5, 6 frequencies. Millikan in 1916. So this is the actual original data from the experiment that he did in 1916. And he plotted the stopping potential versus the frequency. And as you can see, he has labeled it as maximum photoelectron kinetic energy in EV. Okay. And he obtained a straight line. So when you get a straight line, then that fits our proposition that so this comes from half mv square. So EV0 prime is equal to h nu minus E phi, and I'm plotting V0 prime on the y-axis, nu on the x-axis. So the slope is h, and the intercept is E phi. The x-intercept, is it? Sorry, so this is a nu versus, what did I do wrong? Slope is this. Oh, yeah. So the y-intercept, so this got cut. So the y-intercept here, that's E phi. Oh, I hate this. Okay. And from this, then you can, from the y-intercept, you can get the work function. So this is basically the photoelectric effect. Simple enough. Now I'll just introduce the Compton effect. So what is the difference between Compton effect and the photoelectric effect? So in the Compton effect, again, you have light incident on matter, and then the light gets scattered. So it's a little bit different. So in the sense that it is not an electron which is being emitted from a solid surface, as in photoelectric effect. Here, this is simply a scattering of light from an electron. Now, this electron may be inside a metal, but what you're doing is you're detecting the scattered light. So it's not a light absorption leading to emission of electrons. It is a light scattering leading to also scattering of the electron, which is free. So there is a target electron at rest. Okay. ideally, I mean, in an experiment, it would not be a single electron sitting somewhere, but that is how it behaves. So it's a really, really loosely bound electron somewhere. Okay. And you have light that is incident on it. And then what happens is the electron gets deflected and the light, so this is the recoil electron, and then the light, which had a wavelength of lambda I, is then sort of reflected or scattered, to be more perfect, with another wavelength lambda f, where lambda f is larger than lambda I. Okay. So the wave loses some energy and transfers it to the electron. Okay. And then using the principle of conservation of energy and momentum, you can find out how the like how much the wavelength of the light shifts, what angle the electron will be deflected by, what angle the light will be deflected by, etc. Okay. So this is the Compton effect. And okay. So should I start the derivation today? Let me see. We only have 15 minutes.
Ma'am,
Yeah?
ma'am, I have a small question, maybe
Yeah.
a bit trivial. Ma'am, this Compton effect, the electron being loosely bound or a free electron at rest, means that property means that condition itself lets the photon to change its wavelength, right, ma'am? Like if it was bounded, then the states of energies would have been quantized and some partial energy taken out from the the photon, and releasing some of it won't have been possible.
Exactly. You are right. Yeah, you are right.
Okay.
So like in the photoelectric effect, you had a bound electron. So then you had to supply energy equal to at least the binding energy in order to release it. But here the electron is free, so it can, so it has a continuous energy distribution and it can take any energy. So that's why you can, it absorbs some part of the energy and the rest is, remains as light, just going in a different direction.
Is this experiment conducted at something like 0 Kelvin or something, close to 0 Kelvin or something like that? Because it's always, because of temperature, there will be random motion of that electron, right? Like it will be vibrating constantly. So
yes, that is true. So the Compton effect, if you want, so no, it is not. Well, the experiment itself, as far as I know, is not done near 0 Kelvin or anything. It's a normal like room temperature or maybe just a little bit cooled temperature experiment. But a large part of the explanation can be provided by considering the electron to be at rest. If you want really accurate results, then you have to introduce relativity to it. We will also actually put in relativity to it, actually. And then we will, do the derivation. So the relativity part will come in, but the vibration part or the motion part,
this is the thermodynamics part.
Yeah, so that part I am not sure. I mean, do we consider it? Not really. I think now that you mentioned it, the argument is probably that the light travels very much faster than whatever motion the electron is executing. So considering the electron to be at rest is not a bad approximation.
Okay. Okay.
Yeah, I think that is probably it. I have not thought about it before. Nice question. But yeah. Okay, so this is the Compton scattering effect.
Ma'am, but if
Yeah.
ma'am, if it was even like traveling slightly also without considering the light, then also, ma'am, it will have some energy, no? Some extra residual energy in the electron.
The electron, yes, it would have some sort of initial kinetic
So,
energy.
ma'am, it won't mess up with the results.
No, I don't think so. I mean, we can try maybe with a little like adding some sort of kinetic energy to the electron initially, but I think that would just remain like whatever component of the uh, velocities remain in the direction in which it is uh, deflected. I think it would just add on to it or something. It probably does not affect the results so much. I cannot say 100% for sure, but I think assuming the electron at rest gave sufficiently good results to match experiments. I'll look into it. Okay, I'm not sure, so I'll have a closer look at the experiments. Although I don't think it was done close to 0 Kelvin. I mean, it was done long time back, so unlikely. Okay. Anyway, so this is the Compton scattering. We will do the derivations. I will not start it today because it's a long derivation and I don't want to leave it in the middle. So I'll do it on Tuesday. In fact, I think I will just take in the last 10 minutes, I will just skip Compton scattering and complete the hydrogen atomic spectra because that's something you already know and it's not a big deal. And next class, I'll show you the derivation for the Compton scattering. So the hydrogen atomic spectra is the next experimental observation which could not be explained by classical mechanics. Although it is one of the very first observations that was made in the like late 1800s, early 1900s. So what was so remarkable? So when you did or recorded the absorption spectrum of the hydrogen atom, what you got were discrete lines. Okay. So when you do so here you have a discharge tube which is generating a whole range of light, okay, from the hydrogen atom. So this is so this is basically the emission spectrum setup. I'm sorry, I said absorption spectrum. So this is a setup for an emission spectrum. So there is hydrogen in this discharge tube, and it is emitting a set of radiation, which is passed through a slit and then diffracted across a grating to separate out whatever frequencies are present in that light. And then you obtain the spectrum on some sort of photographic film. So this is an old setup, of course. So this is an old setup. So this is shown to be a photographic film. Nowadays, of course, you have again conversion to photocurrent and then you plot it on a computer. Okay. But then if you have a photographic film, you basically literally end up with a spectrum that looks like this. Okay. So you have sets of lines from the emission spectrum. And the experimentalists who did this, like different people discovered different parts of this spectrum. and the series are named after them. So there's the Lyman series, which is in the UV range, the Balmer series, which is in a little bit in the UV and mostly in the visible range. Then you have the Passion series in the infrared range. Okay, and then you have Brackett and Fund in the far infrared, so longer wavelengths. And then, but these lines that you end up with over here, they don't correspond to any sort of classical picture. So in a classical picture, you should have again got a continuous spectrum of light. Okay, because there was no reason for the energy of the hydrogen atom to be quantized, as we say now. Because you see, at this point, even the atomic structure had not been resolved. So these experiments were before Bohr came up with his atomic structure. And Bohr, actually, he did not talk about quantization, but the model he proposed actually required quantization, right? He said that you have certain orbits of definite energy, which means that the gaps between these orbits are of fixed energy. And when the atom jumps, or when the electrons jump between these levels, they can only emit certain frequencies of energies corresponding to the gaps of these levels. And that leads to a line spectrum. So he said all this, okay, but he did not mention quantization, which is, but this was, if you remember the timeline, simultaneous with Einstein and Planck and their concepts of quantization. So these sort of fit together. Okay. And people realized that even the atomic spectra relied on the concept of quantization of energy levels. Here it is of atoms. Okay. So for Planck in the black body, he was talking about quantization of energies of a heated body. Okay. Here it is of an atom. So in various domains, the concept of quantization was popping up. And in photoelectric effect, again, it was the quantization of energy of light. So people were realizing that this was a very widespread phenomenon. There was something funny about microscopic things. And then, of course, Rydberg came up with his formula. So like I said, this is an empirical formula. So he came up with this to fit experimental observation. There was no derivation for it, so to speak. Okay. And so what does this Dredberg formula involve? So it tells you that the inverse of the wavelength, lambda, is related to the energy levels in the hydrogen atom. So what he said was that there is a final energy level, NF, and a initial energy level, Ni, and the difference of 1 by Nf square minus 1 by Ni square multiplied with a constant, which again he determined from experiments, gave you the inverse of the wavelength of the line that you found in the experiment. So he observed this, okay. And if you have a hydrogen-like atom, sorry, 1 minute. Yes, so if you have a hydrogen-like atom, which means you have a 1 electron system, but the nucleus can be heavier, so something like helium plus or lithium 2 plus, then also you can write the same formula for their emission spectrum, which involved something called Rm, which is defined as this. I'll tell you exactly what it means. And multiplied by Z square, where Z is the atomic number. Okay. And what is Rm? Rm is basically a constant called R infinity, which is basically quite similar to RH, just slightly different, okay, from RH. So these are similar but not exactly the same. Okay. Multiplied by 1 minus ME, which is the mass of the electron, and capital M is the total mass of the atom. So why is this constant called R infinity? This is called R infinity because if the nucleus had infinite nuclear mass, then Rm would be equal to R infinity. Okay, so if it is infinite nuclear mass, M becomes infinity. So Me by M is 0 and Rm becomes R infinity. So R infinity was called the constant for infinite nuclear mass. So these two, you can find the Dredberg formula in two alternative forms. So I just wanted to clarify what they meant. So I believe in school you have learnt this. In school you have learnt this first one with RH, but you might come across something with R infinity as well.
Ma'am,
Yeah.
now we are having class at 6.
You're having class at 6? Okay, fine. I am done, as you can see. So I just one more sentence that. So the Bohr had proposed circular orbits, and then when Bohr and Sommerfeld extended their theory to elliptical orbits, they were also able to explain the fine structure of the hydrogen spectrum line. So here you see, you only see the broad lines, but if you zoom into them, there is a fine structure. And once the circular orbits were changed to elliptical orbits, we were able to explain that as well. Okay. Yeah, and this is only for 1 electron atoms, like I said. So hydrogen or hydrogen-like atoms. Okay, thank you. So you can stop the recording.
Ma'am?
Yeah?
Ma'am, actually, I cannot share the recording with anyone. Ma'am, could you please give the access? Because otherwise people can't see. If I forward the mail, I get the recording. If I forward it, they won't be able to see. But if I give them the access, they would be able to see. I had the access before, but now I don't have it anymore. So
okay,
I couldn't share the
didn't
last
change
days.
something.
Last day's recording also.
Okay, I'll see. Since it's like stored in my Google Drive, I'll change the permission. Otherwise, I always upload to YouTube. Okay, there may be like sometimes a delay of a day or so.